Welcome to the course Evolution of the Earth and Life. Today we are going to learn about the development of atmosphere and ocean. We are going to concentrate in this time region of Hadean, which goes around till 4 billion years, starting from around 4.6 billion years, and then also Archean, which ranges between 4 billion years to 2.5 billion years. Some of these range of time we are talking about, some of it has the rock record and some of it doesn't have the rock record, and we are going to be talking about the source of information through which we are interpreting the existence of atmosphere and ocean. Before we talk about atmosphere or ocean, we have to first understand what was the condition like during Hadean. So, during Hadean, at the beginning, the Earth was being impacted by a number of asteroids, and that constantly melted and remelted the very top layer of the Earth. As a result, at the beginning, probably there was not the formation of the crust because the Earth was way too hot. But eventually, as it was cooling down, the crust started to form. Now, the information about the formation of the rocks, minerals, all come from a single type of mineral which is called zircon. These zircons are found in younger aged rocks, but when we date these zircons, they indicate an age which corresponds to Hadean. So, in terms of the physical record of Hadean, we have only these mineral grains, but these mineral grains tell us a lot. So, we know by looking at other planets also that as they get older, they cool down because it's following the second law of thermodynamics, where if something is hot, it's going to try to dissipate the heat, and because the outside, the space is much colder, it's going to dissipate the heat from inside, and for the Earth, it's primarily done through convection in the mantle and in the core. So, eventually, with time, it's going to cool down. Now, as a result of this cooling down, there would be some minerals which will start to form out of the magma, especially when we are talking about the mantle. Now, following Bowen's reaction series, the first minerals that are going to form would be the olivine, and eventually they are going to create olivine rich rocks which are called peridotite. But the peridotites are very heavy, dense, and therefore they cannot be floating in that magma. They are actually much denser than the magma, and therefore they are going to settle down. And probably this was the mechanism by which we started seeing the separation of the mantle from the very top layer. Now, the second phase where things started to develop, the second phase of rocks of distinct composition, would be when the magma has cooled down substantially and at a relatively lower temperature compared to the temperature where olivines crystallize. We will start seeing the crystallization of pyroxene and plagioclase feldspar. So, if we look at Bowen's reaction series, we are talking about a temperature zone somewhere around here. And that will create a particular type of rock which is called basalt. And these basalts are light enough that they can create a floating pattern compared to the magma from which they are forming. As a result, probably there was a situation where on the very top of the Earth, the very surface of the Earth was covered by these basalts. And it's quite similar to many other planets within the inner planet system, where we see a large amount of basalts. Now, these basalts are what creates oceanic crust. So, the oceanic crust was forming. But this pattern of cooling down and cooling down of the magma also involves some release of gaseous material. So, even today if we go to the volcanoes, we will see that the volcanoes release a large amount of volcanic material such as magma, which is in the liquid phase. It also erupts some of the solid materials such as pyroclastic material, ashes and then debris, pyroclastic materials. But then it also releases a number of volatile material, gaseous material. So, the early phase of the earth was not different. It was also releasing a number of gaseous material as it was cooling down. So, it was cooling down, it was forming this oceanic crust, but it was also releasing an amount of gases in the void. Now, how do we know about what might have been the materials that were being released at the beginning? One important source of information was the study of meteorites and the materials in space. So, if we study the meteorites, we will often find that their composition suggests that they have large quantities of water as part of the mineralogy. They also have organic compounds and sometimes other gases trapped inside them. Because we know that the initial composition of the earth was very similar to the meteorites, it's not a great leap of faith that we can imagine at the beginning, as the earth was cooling down, it will also release some of these volatile materials, some of these gases. So, when the rocks melt, these large amount of gases will be released, and this is what's called a volcanic degassing. And this volcanic degassing is not a feature of only early earth. As I just mentioned, that volcanic outgassing can be seen even today. So, in active volcanoes of today, we can see that often they release carbon dioxide, water vapor and sulfur dioxide. Sometimes if these are dormant volcanoes, if they are slowly releasing material, not with a very high amount of magma, often they release carbon dioxide, water vapor, but also sulfur dioxide and sometimes H2S, hydrogen sulfide. If we think about the hydrothermal vents, there we also find carbon dioxide and some hydrogen sulfide. So, these are constant things that can be removed or that can be released from the magma through these volcanic activities. In early earth, probably these were the primary sources of the formation of the atmosphere. This volcanic outgassing from the earth's interior is still taking place. And if we can calculate how much is being released today, it also gives us some understanding of how much is there. In fact, in some calculation, it says that close to half of the earth's carbon dioxide and water is still in the interior, probably in the mantle. Now, what is the form of it? The form of it is actually trapped inside the minerals. So, there are various hydrous minerals which carry some of these water, and when they are going through high temperature change, especially melting, they release these water as a water vapor and also carbon dioxide. So, these are primary components that can very easily come from the Earth-like planet through the primary degassing. Now, part of it probably was lost because of this major impact. During large impact, when Earth lost part of its initial volume of the planet Simmels, probably it also lost some of the attached H2O and CO2. But at the same time, during the phase of Hadean, after the formation of Moon, it was also cooling down and retaining some of these original composition of the volatile. The other controlling factor that decides what's going to be there in the atmosphere is the size of the planet and how far it is to the sun. Now, if the size of the planet is really large, it has a large gravity or gravitational force. As a result, it will tend to attract or tend to keep even the things which are lighter gases. If it's too small, the gravity is not powerful enough, it cannot retain things which are lighter. As a result, if we look at the moon, it is too small and we don't find all the gases that were probably the product of initial degassing escaped, because the escape velocity is too low. Now, if we look at the larger planets, some of the planets which are towards far away from the sun, their size is so big and so strong gravitational force, they even attract things which are very light gases and therefore can create a very thick atmosphere. But Earth is a planet which is not as small as Moon, but not as large as, let's say, Jupiter. As a result, we have a specific escape velocity of 11.2 kilometers per second. What that means is there are some gases which are difficult to keep in the Earth's atmosphere because of the gravity. One such gas is hydrogen. So, probably at the initial phase there was quite a bit of hydrogen as part of this degassing process. Some part was produced because of the breaking down of water vapor, but those are difficult to keep in the Earth's atmosphere simply because the gravity doesn't support it based on the size of the planet, and therefore those were lost in space. Now, if we look at the primary composition of the initial atmosphere, it definitely had nitrogen, carbon monoxide, water vapor, ammonia, carbon dioxide and methane. Important point in this particular plot is the size of the bubble actually shows you the relative concentration of each of these gaseous elements. So, what we see is the maximum or comparable amount of carbon dioxide and nitrogen and some amount of water vapor, and then a relatively similar amount of carbon monoxide, ammonia and methane. And this made this atmosphere weakly reducing atmosphere. Now, what is very important at this point to realize is we do not really see any oxygen, and that we are quite confident about this conclusion, that both Hadean atmosphere as well as Archean atmosphere did not have any oxygen in it or substantial amount of oxygen in it. Important changes that we see when we compare with the modern atmosphere, that the nitrogen amount pretty much remained similar, but we see a very high concentration of oxygen and the carbon dioxide is much limited when we compare it with the Hadean or Archean atmosphere. Now, the question is exactly when did these things happen? Because we think that the rate of temperature loss, rate of heat loss from Hadean to Archean has been a steady thing. So, probably this kind of an atmosphere was there very early on even in Hadean. And once that happens and this hydrogen, this water vapor plays an important role in the next subsequent development. And that subsequent development is the water. Liquid water is one of the most important aspect of the earth. The life depends on it, and there are various processes that take place on the earth which are completely dependent on the liquid water. Now, what controls whether a planet is going to have liquid water or not? As we saw that the initial degassing probably is going to create water vapor anyway. So, probably that was true for all the planets. Some planets couldn't support it if they are very small, such as Moon, then they are going to escape. But a size of a planet like Earth, they can support these water vapor, and that can be in the atmosphere. However, whether it is going to be in a liquid phase or not is determined by the distance from the Sun. If it is too close to the Sun, it is too hot to retain the water in the liquid phase, and probably it is always going to be in the vapor phase. The other option is if it is too far away from the Sun, such as Saturn, then the liquid vapor will not be there because the temperature is too low to support the water in its liquid form. So, it is going to be in a frozen state. So, Earth is in this particular state where it is a perfectly placed planet, a distance from the Sun which is not too hot or not too cold to retain the liquid water, and also a size of it is not too small where it can lose the water vapor to space. And that is one of the very important point about the Earth's size, mass and distance from the Sun that worked in favor of the development of life also. But how do we know that there was liquid water during even Hadean? So, as I mentioned before that zircons, which are ZrSiO4, zirconium silicate, this is a mineral which has been found from various parts of the Earth, and some of them are in very old rocks. One such rock is from Jack Hills of Western Australia, but more than the rocks they come from, these mineral grains show even older age. Some of these ages date back to 4 to 4.4 gigaon. Gigaon basically means billion years from today. So, billion years ago. So, 4 to 4.4 gigaons are the ages of these zircons, and they show a specific geochemical signature that can support liquid water. Now, the details of how we know about it involves a little bit about isotope geochemistry. So, we know that every element has proton, neutron and electrons. Now, depending on the proton numbers, the mass number is determined. So, for example, if we look at oxygen, it can have different mass numbers. The regular oxygen that we see, it is the O16, but there can be a bit of heavy oxygen which is O18. So, the difference between the two is basically the number of neutrons. The proton number stays the same, it is just the neutron numbers which are different. So, O18 has extra neutrons and O16 does not have them. Now, the ratio of these O18 and O16 in a particular oxygen bearing mineral is dependent on what are the changes it has gone through, especially the phase change. For example, if water, which also has oxygen in it, if it goes from liquid to vapor phase, there are changes in this O18 and O16 ratio, and looking at that we can figure out whether it has gone through this vapor phase, it has gone through from liquid phase to vapor phase. Now, using this criteria, we can also look at all zircons, especially the zircons that we can find from the mantle, which clearly do not show any sign of liquid water, and it shows a temperature which is very high, and other type of patterns which are at liquid water temperature level. a temperature at which the liquid water is stable. Now, if we look at these particular grains which were found from 4.4 gigaions, these are these mineral grains and these mineral grains and these ones. Now, if we look at this line, what it shows that if we plot this del 18O, which basically means a ratio of 18O and 16O in a particular convention, we see a signature which is distinct from the ones which are corresponding to mantle zircon, and this basically indicate that they have formed at a relatively lower temperature, and that lower temperature can support liquid water. More important another supporting evidence is, by this time we also started seeing some of the examples of granitic rocks, and subsequent to that we started finding examples of granitic rocks, and these granitic rocks are very hard to form unless the temperature has cooled down subsequently, and also there is water which can lower the melting point. So, combining all of these facts, it is quite clear that even in Hadean there was liquid water. So, the temperature cooled down subsequently after those impacts. The crust has formed, especially crust which is the sea floor, and then we also have atmosphere, and this atmosphere is condensing the water vapor into the liquid form. So, volcanic degassing led to the release of water vapor. That would be one source of water, but the other source of water is some of the water that have come from the volatile rich bodies of outer solar systems such as comets. Even today when we sample comets, we find that they have a significant amount of water mixed with dust. So, these are the icy materials mixed with dust that often come in a periodic manner, come close to the earth. One of the common ones is Halley's comet. So, they can bring significant amount of water. So, both of these were probably the major source of water on the earth. Now, in early Earth's history, the earth was probably too hot and it had a thick atmosphere. So, atmosphere was probably the first one to form during this degassing. Some of it was lost based on the escape velocity, and some of it was retained. And then the surface of the planet was hotter than the boiling point of the water, and therefore, it was not possible to keep the water in the liquid form at that phase. So, we are talking about development of the atmosphere, then the development of the oceanic crust, but eventually the surface cooled down enough where the water vapor could start to condense and rainfall start to begin. Now, when the rainfall started to begin, the surface was already made and there were significant depressions in the surface also. We are talking about oceanic floor, and later they got filled up by this rainfall and as the water started to accumulate, and that was the ocean. So, an ancient ocean likely covered the entire planet 150 million years after the formation of the earth. So, if we take 4.6 billion years as the starting point of the earth, by 4.4 billion years ago there was already an ocean, and the sequence of events was first the atmosphere, then the formation of the oceanic crust, then the ocean, and probably around that time or subsequent to that we will start getting the development of the continental crust and the continents. Now, do we actually have direct proof of these early ocean? So, now we are going to focus on the rock record, because so far we were talking about only the records that we can infer from Hadean zircon grains, but now we are going to look at the rock record of Archean. So, Archean starts from 4 billion years ago, and we are going to look at rock records which are younger than 4 billion years ago, and we are going to see whether there are direct proof of water. So, one of the good places to look for Archean rocks are a complex, it is called Ishua, near western Greenland. It is situated in western Greenland. The rocks that we find there are generally 3.7 to 3.8 gigaeons old, and these are the two types of rocks that I would like to share. The first rock is a seafloor sedimentary rock which has later been metamorphosed to some extent, and these show an example of how sediments are being deposited under the seafloor. It is very difficult to form these kind of sediments or sedimentary rocks or metasedimentary rocks unless there was flowing water which carried the sediments and deposited under the ocean, where it can later convert to a rock. A more direct evidence is from this 3.8 gigaeon old pillow basalt from the same formation of Ishua from western Greenland. Now, what are pillow basalts? So, these are basalts which form underwater. Even today, if we look at the formation of underwater volcanoes, especially if we look at Hawaii, often what we see is underwater when the volcanoes erupt or near the mid-oceanic ridges or near the plumes. If it is underwater, the basalts start to form a crust, but because of the water it forms very quickly while the core of this molten material is still hot. So, they puncture this crust and they ooze down and form another pillow like shape, and this continues. And these are the shapes of these pillow basalts which can only happen if it is happening underwater. And we start finding these pillow basalts, records of these pillow basalts from Ishua, which is 3.8 billion years old. So, these evidences are a direct rock record that tells us that there was water, there was ocean where these things were forming. Now, we have the ocean, we have the atmosphere. What about the climate? And that is where it gets a bit complicated. So, there is something called a faint young sun problem. What it means is, as we go with time, the sun is getting brighter, and the reason behind it is in the sun's core, the nuclear reaction fuse 4 protons into helium nuclei, and this increases the mean molecular mass and decreases the number of particles per unit volume. In response, the weight of the overlying column presses inwards and the core temperature rises. So, if this process continues over time, the sun becomes brighter. So, it has been modeled that solar evolution models show that the sun was 25 to 30% fainter 4 billion years ago. Now, the question is, if the solar luminosity was less, how could Archean climate remained mild? Why couldn't it be a completely frozen planet? Now, the rock record shows us that if we go with time from the oldest to youngest, there are times when we have glacial intervention. So, these are the glacial times when we have global ice ages, but if we look at the Archean, we really do not see a major glaciation at the beginning. But if we are talking about faint young sun, that means we are expecting to see some very cold temperature, and we do not really see that. Why might that be the reason? And one reason could be the contribution of the greenhouse gases that were present during Archean. There is an interesting cycle that goes on which is called a carbonate silicate cycle, which controls the overall temperature and the greenhouse condition of the earth. We understand that the Archean carbon dioxide concentration or partial pressure of carbon dioxide must have been quite high, and that activates the earth's carbonate silicate cycle thermostat. It is called a thermostat because it sort of has this interesting balance which can keep the temperature in a relatively shorter range. Let us see how it works. So, generally when the rain falls, it basically reacts with the carbonate rocks, and for the carbonate rocks, the carbon dioxide with water creates a light acid, and it reacts with calcium carbonate and releases the calcium and bicarbonate. When it is a silicate rock, it is the carbon dioxide water and reacts with the silicate, releases the calcium bicarbonate and then also releases silica, and that silica can stay. It can be carried as quartz, it can be finally deposited in the continent or in the marine realm. Now, what happens when we are increasing carbon dioxide? Well, one source of increase in carbon dioxide is through degassing. This degassing can add more carbon dioxide in the system, in the atmosphere. Now, more carbon dioxide means temperature can go up because it is a greenhouse gas. How does it get balanced? Now, the way it gets balanced is when the global temperature, if the global climate warms up, if it warms up too much because of, let us say, higher carbon dioxide, then the rainfall is going to increase, and if the rainfall is going to increase, it is going to have higher rate of erosion, and those erosion actually takes the carbon dioxide and basically releases calcium and bicarbonate or sometimes silica, and therefore it draws down, it reduces the amount of carbon dioxide from the atmosphere, and therefore finally the earth cools down. The complete opposite thing happens if the global temperature and carbon dioxide both are low. If they are low, then the rainfall is not too much, then it is not too much of erosion, and therefore the carbon dioxide is not getting drawn into the erosional cycle, and therefore it will keep on accumulating, and therefore eventually it can lead to slightly elevated temperature. So, this is how the temperature is kind of being balanced, and the rate of silicate weathering is kind of going to adjust itself depending on how much carbon dioxide is in the atmosphere and what is the temperature like. So, what we understand is during Archean, because of the high carbon dioxide, even if the sun was fainter, this led to a constant maintenance of temperature, and it did not lead to a very low temperature because of this maintenance by the weathering pattern, and that kept probably the temperature between 0 degree to 40 degree centigrade, and that is how the Archean climate remained milder and not created a completely ice house effect or completely glaciated earth. So, in today's class we learned something about how the ocean, atmosphere and the oceanic crust formed at the beginning of the earth. What was the composition like of the atmosphere during Archean? What was the source of water of the ocean during Archean? Do we have direct proofs from the rock record of Archean that tells us about the flowing water and the ocean? We also learned how the climate was during Archean, and we learned how the carbonate silicate weathering pattern can work as a thermostat and control the temperature of the and the climate of the planet even if the sun's luminosity was low. Here are some of the resources that I used for developing the slides, and here is a question for you to think about. Thank you.